In this video, we provide supplementary visual content to our iGraph submission. In order to enable autonomy of large-scale construction machines, a reliable state estimation and localization is needed for this particular use case. First of all, smooth and consistent state estimates at high frequency are required in order to perform control for complex tasks reliably. An example of this can be seen in the control of the chassis to traverse over uneven terrain. Second, an accurate localization is required for many high-level robotic autonomy tasks such as navigation, planning, and mapping. A given example can be observed in the task of robotic embankment, for which landscape architects are creating global plans in the world frame prior to the robotic operation. Because of the complexity and diversity of the operational environments of excavators, it is essential to also handle special events such as sensor loss, in particular the loss of GNSS in the presented use case. For state estimation and localization in the construction task, one can observe accurate and smooth estimates of the state estimator. In particular, for the case of GNSS loss, the proposed approach remains stable while CIF is becoming unstable, with occurring jumps due to inconsistency in the GNSS signal, as it can be seen in the green curve of the left video. Additionally, the proposed approach also works in realistic construction scenarios, such as conducting a task at one place, moving to another location, and manipulating objects there. Note that manipulating objects strongly excites the cabin, which is nicely captured by the prediction of the estimator. For the navigation task, a comparison of the proposed approach and CIF is presented for the usage of mapping. In the left video, the current state estimate and the accumulated map are presented. On the right, the map created by CIF is shown. As long as GNSS signal is present, both maps are equally good. But as soon as GNSS becomes absent, in this case because the excavator is partly covered by trees, CIF becomes unstable while our approach still remains consistent due to the LiDAR pseudo-global factors and the dual graph design structure. When GNSS returns, the global estimate is updated by switching back to the main graph. Note that this jump, happening here, is introduced in the world to Autumn transformation, and hence the estimate in the Autumn frame remains locally consistent, making it suitable for control. Thank you very much for your attention.